let me quickly thank a few people. So first of all, thanks to EngFlow for organizing this and paying for my flight, because that's the best part. And second, I want to thank Hunter and Spencer. Where are you guys? Without which this talk would not, this whole meetup would not have been possible. This was all organized in front of quite a few peers in Munich last year. Also paid by EngFlow. And today, if the screen works, fantastic. We're going to talk about Bazel's platform and Toolchains. And how many of you know about Bazel? Quick show of hands. Yeah? Yes, I can skip a whole section of the talk. That's fantastic. And so you may be familiar with this idea of platform and Toolchains, but why am I here to talk about this? So I'm Antonio Di Stefano, and I'm a solution engineer at EngFlow, which means that I do sometimes do coding, and sometimes I try to sell our product to people and make it work, if possible. I guess that's the solution part of the title. And I love making all kinds of developer tools, love containerization and system programming. Also love ducks, beer, travel, and metal, a few of which you might have guessed from either the t-shirt or the fact that I'm in Japan. I do really hate YAML, especially the fact that you have more than 60 types of ways to write a string. And my only question there is why? You can reach out to me, antoniodencho.com, if you have any questions, or you can sign up to our newsletter if you want to see some really cool or weird hacks or people trying to run Snake on Bazel, which God knows why I did, probably the beers. So what is this talk about? So as the title implies, it's about platforms and toolchains. But most importantly, it's about cross-building and testing software with Bazel. You can do a lot of things with platform and toolchains. That's also like the mechanism that partly allows you to have really hermetic and configurable builds. But in this talk, I want to focus on the cross-building and testing aspect of things, which tends to be extremely hard with pretty much all build systems. But really also allowing you to create hermetic builds. And there's also the feature that makes it possible for Bazel to remote things to make them extremely cacheable. So this set of features is extremely important to the Bazel ecosystem. It is really what allows you to build on pre-existing code. Whereas rules allow you to completely extend the build system. I feel like you can think of platform and toolchains as a way to hook yourself up into the existing things and completely change the behaviors of how they work, even with native things. So I'm actually going to focus and have a demo about how to get a cross build with C and C++. And I'm going to target Windows, which is pretty infamous in the Bazel ecosystem, and even run tests on Windows. But we're going to see that later. So now everybody show their hand up. So I'm going to do a quick introduction of Bazel. Bazel was born as this thing called Blaze, which some of the people in the room do know because that's literally what they use every day. And that's their internal build system. It's engineered for speed, correctness, and having lots of flags, of which the syntax of and semantics of are obscure to everybody, including Bazelers. It's able to distribute actions in a completely distributed system, which is remote execution, which is what my employer EngFlow provides for our customers. And that allows it to scale up to sizes where really no other build system could get to. If you ever tried building Chromium for real on your laptop, you know what I'm talking about. I don't even know how long it takes nowadays, probably days. But if you scale it up and have hundreds of executors or 1,000, then the thing becomes much, much faster. You can parallelize instead of up to 8 times, you can parallelize to 1,000 of times. So a quick show of what a Bazel build looks like. And even just in this simple slide where we build a simple binary and we add a test, there are lots of different concepts that we have. So the first is this CC library and CC binary and test being rules, which are the extension mechanism that Bazel uses to hook you up into the internals of the build system. And rules are basically scriptable extension of the build systems. So CC library will generate the actual actions that do compilations, do linking, and so on, but also provide metadata for other rules to consume. And you can think of lib, bin, and test as instances of these rules. And these instances are called targets, so something you can target within the build, or refer to as a dependency, as we see in bin, which depends on the lib library. And the same for the test. Any question here? Like, does anybody have any question? That's great. And now what are platform and constraints? So I think it's easier to explain it starting from constraints, because that's the core concept on which platforms build on. And constraints are pretty much what the name implies. There are a set of dimensions that we use to configure a build result or a build environment or a test environment to behave in a certain way. If we want a binary that targets ARM64 and we want it for Windows, then we're going to have a constraint that says the OS is Windows and the CPU architecture is AMD64 or ARM64 or whatever we want. And platforms are like the counterpart to that. So you have a collection of constraints within a platform, and to that you associate certain behaviors. And in Bazel, you have 3 platforms. The target platform, so the one you're building for or testing for. The execution platform, the one that is doing the actual actions like compiling and linking and testing. And then the host platform, which for most build systems is kind of the same as the execution platform, but for Bazel can be different. So it's the actual platform running the build. So your laptop, in this case for me, would be Linux. But because you can have a different execution environment, for example, you could have a Windows machine running at the actual compilation actions on Linux, maybe with a compiler like MinGW, and then you can actually have a mix of execution environments as well, which is actually what we're going to do. And this is what a platform looks like. And the way, this is what a constraint and then a platform looks like. The first thing that you do when you create a constraint is declare this name of the constraint. You kind of create a family of constraints, and then you have the various instances. Like if you have the constraint compiler, then you can have various values like GCC or MinGW, which are the ones we're going to show. And then you can actually reference them in the platforms as we've done now. So we got the Linux x86 build, which uses Linux x86, but also is implying that the compiler used is GCC. So this platform is only going to be selected if the constraints that we have are satisfied. And same for the Win x86. So if we set certain constraints, one platform is going to be picked versus the other. And this is what allows us to, for example, configure toolchains for a specific platform. And toolchains are not a Bazel-specific concept. If you've used any other build system or like any other toolchain, I guess, you've heard of it. So it's literally a set of tools that you can use to do a certain action. So if you want a C or C++ toolchain like GCCs, that's what allows you to get from C code and get to a binary or get to a shared object library and so on. And rules are pre-configured to use these tools under the hood, but do so in a way that allows you to configure how they behave. So for example, in C++, in the Bazel C++ rules, which we're going to look at, you can declare a toolchain and say, like, for example, this toolchain has these features that you can enable, and these features are wired up with these flags. And the binary I used is this binary rather than the default system GCC. Whereas other build systems like CMake, you just specify a set of properties, and it's a less dynamic mechanism. It's much, much simpler, but it is far, far more configurable to use what Bazel does. And so like Bazel's mechanism, though very complicated, allows you to do pretty much whatever you want and extend it as much as you want. But it also means that it varies per rule set. So toolchains are pretty much defined on a per rule set basis, and they can have widely different semantics that are applicable to the thing that that specific rule set is trying to build. So they don't exactly look the same as they would do in other build systems. They're going to look somewhat widely different. And you can find, and some of the really interesting ones are the ones you can find in the native rule sets themselves, like the C and C++ ones or the Java ones. But then you often have to dig into really obscure Starlar code. And I wanted to take the rest of the talk to actually look at what these platforms and toolchains are. Because most of what I've explained up to this point, you can kind of find in documentation. And what I struggled to find while writing this talk was actually like good examples, especially on cross-compilation, because like that seems to be the most common use case, right? You want to be able to build from your machine, and you want to target whatever you want. distribute builds on the cloud because you have RB, you might as well use it. And you have remote caching, you might as well use that one too. But then the question is, how do you reconcile these things, right? How do I get, how do I write my C++ code and build from Linux to Windows? And then when I've built it, right, I have a binary. What can I do with this binary? And like the thing that all developers need to do in that case is test it, right? And you have automated tests, but you also need to configure a toolchain now that allows you to run the automated test without writing some really obscure macros that wrap things up in another binary and do some weird black magic. And they also need to update stuff for security, but we ignore security here. Don't tell the CTO, please. Is this recorded?
No.
Thank you. It's gonna be cut though.
Yeah, the recording there is
No, no.
fake.
Yeah, that's actually I've put that on the screen. It's just an icon. We need to edit this talk later. And so I wrote a very simple library, which is it behaves differently for Windows and Linux. It writes hello world to a file. The file name is this one. And it's really bad. Like I actually had ChatGPT generated because I couldn't be bothered. That's not the goal of the talk. And yeah, ChatGPT is not going to replace us all. It's just going to replace Skip. And then there is just a main file invoking this function. And that's it. If you look at the build definition, it should look fairly simple. Like we have a CC library. And then we have a multi-platform CC test and binary, which are just macros using some really obscure feature we're going to look at later if we still have time. But you could just think of as another CC binary. I can't type today, all right? And another CC test, right? And that should be what the build looks like. I don't want to create any additional macros. I don't want to create any additional rules to do something that Bazel can already do. I just wanted to tell it how to behave under the hood. And for this reason, we're going to have two different tool chains. First of all, we're going to need a tool chain to compile. And I've picked MinGW, which is this open source project that basically has this no tool chain for Windows. I think that's part actually of the acronym, which I completely forgot, despite reading right before the talk. And we also want this tool chain to be completely hermetic. We don't want the user to have to set up anything. Because if you have to set up anything on your system, then any engineer could do it in a slightly different way and lead to extremely confusing, obscure bugs, right? Let's say you have MinGW version 1.8.7612, and then the other guy is like a small patch that makes everything completely different, triggers an obscure bug, and now you're debugging something in the middle of the night because you have a release tomorrow, right? We want to avoid that. We want every single developer to have the same tool chain. And so the thing that we're going to do is that we just download this tool chain during the build, right? So we have a repository rule that downloads the this tool chain from a remote URL, and then instantiate it as a repository, adding a build file and this and an additional custom rule in configure.bazel. The build file itself is quite simple. Just groups the sources, and then creates this this target, which is the actual C++ toolchain, and wires it up using this rule called CC toolchain. Now this rule does some magic, which is different from how you normally configure rules in Bazel, and it's specific for C and C++, which are a bit different from how you configure other toolchains elsewhere. And you basically specify what files do you need, where do I need to find the definition of the toolchain, and so on. And then you say where it applies. So the way I like to think about this is that whenever you write a toolchain, you basically have, you declare what's the type of the toolchain. So in this case, it would be something like cc compiles or something like that. Then you define the actual properties of the toolchain, which is what we were doing with this one. So how it's configured and how to use it. And then finally, when you have these two pieces, you use this rule called toolchain to bind them together and decide where they're applicable. So in this case, this toolchain can be considered applicable when you have a certain OS and a certain architecture that do vary depending on how I'm instantiating it. So for this example, I could download this toolchain for Linux, and I could download it for Windows, and actually use pretty much the same logic everywhere, except one is going to have Windows binaries, the other is going to have Linux binaries. Well, not now. And this exec compatible with will tell it which one to use, right? So if you declare constraints on the and declare the exec the target system to be Windows, but you want and you want it to build on Linux, then this is going to say that Linux and the architecture of the platform that you're using to exec, and the target is Windows x86 64. Now you could imagine this, for example, having to target another architecture, so you would have another Windows, but a different architecture, declaring a different tool chain. And then once you have all of this, so all of this configuration, which we're going to dig a little bit deeper into in a bit, you just need to register it. So first you apply this rule, which downloads the toolchain, configures it the way that we've just seen, and then you need to actually explicitly register it so that it can be discovered. I've only registered the one for Linux targeting Windows because there is already one implicitly defined from Linux that targets Linux using GCC. So I don't need to declare this one. I just need the mean GW one. And that allows Bazel to discover it through that mechanism of matching on constraints. So let's take a quick look at how it's actually configured. It's not this one. So the magic is all basically in here. What you do with C toolchains is you declare on which action you apply a given tool. So, for example, here I was replacing this with some magical compiler, right? I would just change the path, and it will now start using this path for the action itself. And I'm telling Bazel, okay, it's not applicable for every action. It's just applicable for C compilations versus C++ compilations, right? And to that, you can also add features. So, for example, in this case, it's a bit preposterous, but I'm forcing static linking whenever you invoke the linker because I'm passing the flag -static, which does actually make this talk much, much simpler, but I'm not going to explain why, because it is actually really cheap. It's also a good example, though. And then you just wire all these things up. You declare an identifier and a few other things like what CPU am I targeting. In this case, K8 is equivalent to AMD 64 or x86 64, depending on how you call it. The name of the compiler, and then you just start code an absolute path because you couldn't figure out how to fix this in time for the talk, and you were really tired while on the airplane because it's a 13 hours flight. So, but aside from that, once you've actually figured it out and not hidden it in a to-do, you would actually get a toolchain that is able to run remotely because it's completely hermetic. You're going to get the same setup. You don't need to set up a Docker image for the remote build that does provide this compiler. You get something that works on Linux, yet targets Windows. And also, it's not MSVC, which I think is a plus. And that's the first part, which is partially documented. Again, it's obscure documentation, but it is documented. The really, really, really bad part is that sometimes you have to dig into Bazel. And it's not fun. Like, if you find that fun, we need to have a chat. So it isn't. It really isn't. But sometimes you have to do it, and that's probably the biggest problem that I have with toolchains, is that they can be hidden inside code bases, and you actually need to understand how things work under the hood. So if I have a complaint for the Bazel team, and if there is any Bazel team member here, please document the toolchains, because discovering them takes a lot of effort. In this case, the toolchain that they cared about was, I want to write a wine toolchain so that now that I have the Windows binary for tests, or the actual Windows binary, I can run it. Now, this actually only covers test. There's one little neat trick that you can use at the end to actually use Bazel run using a Windows binary. But I'm going to cover that at the end if we have time. And so the structure of the toolchain looks identical. And once again, we do actually have to look at this Bazel code. And the toolchain that you can use in this case is this CC test info. And it allows you to declare some linking options if you want to link statically always or not. Again, I've hard decoded a lot of stuff here that you really should not be hard decoding, but it kind of works sometimes. And then you basically declare a function that is invoked by the C++ rule set and allows you to return any provider that then the rule actually returns. So in this case, if you want to return a test, what you do in Bazel, you return a binary, right? And that binary is going to be the binary that gets executed. And what I've done with Wine is, first of all, I've not done a fully hermetic toolchain in Wine because I couldn't be bothered. And again, it was pretty late at this point. So I'm using the system Wine installation, which I just said it was a bad idea, but bad ideas are fast. So this is what we're doing here. And you basically just call Wine, this simple Wine script. And yeah, you ensure that X11 is disabled because Wine likes to open UIs, even when there's absolutely no need to do so. This neat little trick of declaring a dedicated Wine prefix, like a workspace in which Wine instantiates its Windows-like file system. And then you just run the command that the binary that you've compiled with all its commands inside Wine. And this is really all there is to it. And once again, you go back to the module, you register it, and now that's automatically discovered. So now you have a tool chain that is able to do a test, to compile, to do everything. And we can try it. I think talked a lot, but if the build doesn't work, then I've kind of failed, right? So let's try doing it. So I was also talking about you may want to Bazel run a binary, and that may not work, right? And you're on Linux, you're just trying to run a Linux binary. How do you make that work? So in Linux, there's this feature called bin format, bin FMT, that allows you to associate either a magic or, damn it.
I really like the arrow.
Yeah, that's wonderful, yeah. You know what we do in this case? Yeah, whoever left, you got it. We act like as if. And look at this sneaky guy. Yeah, slightly different exec root. And we just hide it. Don't think too hard about it. It's just the simplest way to fix this, which is what you do during a talk. And now it's testing on Windows, which takes a lot, because if you're doing something like this, you actually want to make it work, please pre-instantiate the Wine prefix, because it takes like 10 to 15 seconds to just build the Windows-like file system, whereas you could just take it, zip it, and maybe create overlays based on that existing prefix. That would be really, really fast. But fast does not make a good talk. You want everybody to be on edge and think like this is gonna fail. Whereas you look at it, and it kind of works. But now we want to run it to prove that like actually bin format does work. The problem being that I don't remember the name of the binary. Oh yeah, there's some black magic actually happening. I have to put .exe. And yeah, there we go. Actually, one last thing that I would like to look at is if we got the paths of the binaries, I want to show that some of them are Linux binaries, some of them are not. So file, this one is the Linux one. And this one should, hopefully, be the Windows one, which we've also just run. Now, how much time do I have left? Oh, that's great. Yeah, I love that. I'll take that answer any day of the week. And the last thing, which I can't spend too much time on, is this feature of Windows of Bazel called transitions. And the neat little thing is that with transitions and a lot of glue code, you can actually get binaries building for multiple platforms at the same time. You might notice that I've run a single build yet generated multiple outputs. These are called 1-2 transitions, 1-2 plus transitions. In this case, I'm always building for multiple platforms at the same time. The advantage of not doing this within a single build is that now you can actually parallelize even multiple builds at the same time, right? And so using even less resources. Let's say that your build has a bottleneck on linking. So in your build, no matter how much you parallelize it, you always have one linking action that happens by itself, right? If you're building for multiple platforms, though, you could link for Windows, Linux, and whatever you want at the same time, and that's a little bit more parallelism, and you're running everything in a single build, and that can be a bit faster. So there's an advantage to that. Also, you can just run Bazel test ... and be sure that it's building for every platform. So there's also like the cognitive overload that you get rid of by using these transitions. And that's it.